Hi, so this is lecture 8, part 1, speed of EF and partial differentiation. Last time I told you that I am going to talk about one special differentiation, which is actually a partial differentiation. Let's start talking about that. All right. Well, robot. Well, as humans, robot works with its end-effector, right? Grab a tool or a part and bring it or insert it and so forth. So therefore, like painting robot and welding, welding robot and assembly robot. So therefore, need to control EF speed, end-effector speed. Like painting, you really want to control the speed, right? So for that, we control EF speed. How? Of course, joints. Joints are the ones we directly control. So by controlling the speed of the end-effector, we control the speed of, by controlling the speed of the joints, we control the speed of the end-effector. Okay. To do that, we need relationship between joint and EF speed. If you do have a relationship, you can use that relationship to control EF using joint. So like this. Let's start from a simple case. Two-link manipulator, the one we started this lecture with. Okay, this one here, theta 2, theta 1, theta 2, and you have x1, x2, y2. So the speeds are the x2 dot and y2 dot. That's the end-effector speed. And theta 1 dot, theta 2 dot, those are the joint speeds. Okay, start from kinematic equation. The reason for that is that the definition of angle can vary, as we have learned a long time ago. So therefore, let me use a general function f theta 1, theta 2, and g theta 1, theta 2, so that we can apply the result to many different definitions of the angles. Let's compute delta x2 first in terms of delta theta 1 and delta theta 2. So delta x2 by definition is from that to this. This is the theta 1 changes from theta 1 to theta 1 plus delta theta 1. Theta 2 from theta 2 to theta 2 plus delta theta 2. So from here to there, that's a difference in x2. All right. What can we do from here on? What can we do? Well, here is mathematical trick number 2. Okay, do nothing. Mathematical trick number 1 was sandwiching from both sides. That was very handy for computing the limits. But this one here is another very useful tool, mathematical tool, which is do nothing. Aha. Do nothing? Yes. Actually, there are two do-nothing operations. What do you think are the do-nothing operation? Some of you may have noticed. One of them is add 0. Of course, that's do-nothing, right? Or multiply 1. That will do nothing. Okay, those are the ones I am going to use. Okay. So first do-nothing, add 0. Okay. For this one, add 0, meaning you subtract and add exactly the same thing. So in effect, you are adding 0. You're adding nothing, but subtracted, added and subtracted the same quantity. That is a catch. And second do nothing, that's multiply 1. So what do I do? Well, for this one, I multiply delta theta 1 and divide by delta theta 1. For this one here, multiply delta theta 2 and divide by delta theta 2. So I'm multiplying 1 for both of them. Do nothing, right? Okay. And if I divide both sides by delta t, you have a ratio which can be used to compute the speed of x2. So that's delta t is here, sitting here and there, and looks like those are the speeds of joint 1 and joint 2. So now taking the limit. Aha! We just have to take the limit, okay? Whenever you compute the derivative. Okay, dx to dt. In other words, the speed of x2 is the limit delta t goes to 0 of this one here is delta t goes to 0. This one plus delta t goes to that. Okay, so we have two terms here. And since delta theta 1 and delta theta 2 goes to 0, as delta t goes to 0. Right? So we can rewrite that equation into this form. This part, let delta t goes to 0. This part here, delta t does not, well, explicitly come in. So therefore, theta 1 and delta theta 2 goes to 0. Same thing here. So those two will become the speed theta 1 of speed of theta 2. So the problems are those 1 and 2. How we can compute those. And if you look at carefully those 1 and 2, only one of the variables is changed. Here, theta 2 plus delta theta 2 is not being changed. Only theta 1 is changed from theta 1 to theta 1 plus delta theta 1. Here, theta 1 is not changed. Theta 2 is changed. So it's a differentiation. It's similar to what we know, but with respect to two single one of the variables, single variable. There are two variables, but here only theta 1, here only theta 2. So one of them is this, one is this, and two is this. In one, theta 1 changed, but theta 2 not changed. Second one, theta 2 is changed, but theta 1 not changed. So differentiation, but with only one of the variables. With only one of the variables. Here, only two of them. But even if you have many joints, you can do this repeatedly to come up with only one variable. So, don't you think the word partial is a nice way to explain what's going on? So we give a new name for this and call partial differentiation. And give this new notation. New notation, round. Round f round theta 1 to designate, to show that the only theta 1 was changed here, only theta 2 was changed here. Okay, so whatever the variable comes down below here is the single variable which were changed. Okay, so using those notations, we have that. And from this, easily you can say that the dy to dt pretty much the same thing. Instead of f, we use g. That's it. And if you have those two equations, we know that we can put them together into this form. Vector matrix notation here. And this one here, coefficient matrix here is such an important matrix. And so it has a name. This one is called the Jacobi matrix here. And also the determinant of this matrix here is called the Jacobian determinant. Okay? And so let's look at Jacobian more closely. Jacobi matrix and Jacobian. Jacobi matrix is nothing but the gain matrix from joint speed to EF speed. Joint speed is sitting here, and if you multiply Jacobian matrix, then you get the end-effector speed. So it's a gain from here to there. And if Jacobian, which is the determinant, is not equal to 0, then there exists the inverse matrix. We already know that. Okay? So this is J inverse Jacobi matrix. Then the role of EF and joint reverses. Given EF speed, multiply inverse Jacobi matrix, you get joint speed. This is something we really wanted, don't we? We want to control end-effector speed. In other words, you know how end-effector should move. So this one is given. And you want to find out how we control joint speed. So this is a question we really want to have. For that, Jacobian must not be 0, right? So that we can compute inverse Jacobi matrix here. Okay? So if I reverse the way I say it, we can find joint speed for given end-effector speed if Jacobian is not equal to 0. So this statement can tell you how important it is. And because it is very important, so we study what's going to happen if this thing is equal to 0. That is called a singularity. Singularity, the word singularity is used in terms of AI, artificial intelligence, for a different name, but this singularity is really a singularity. I'll tell you why. So when Jacobian is equal to 0, cannot find joint speed for given f. That means even if the end-effector speed is given, you cannot control your robot to realize that end-effector speed. That means that you don't have enough freedom to do that, right? So that's loss of freedom in motion. And for that, technical word for that is DOF, degrees of freedom, loss of degrees of freedom. That's what's happening when Jacobian is equal to 0. So singularity should be avoided, right? Naturally, you want your robot to move around freely, but if this happens, you cannot. So this should be avoided. An example of Jacobi matrix Jacobian and singularity using two-link manipulator in the next lecture. Next lecture, I will show you that. But before that, what I want to do is to show you what kind of things happens if you have more joint. We had only 2 joints, but suppose you have many end joints. And I had not only x, y, but z, meaning that you are talking about 3-dimensional motion here. Kinematic equation of hand-link manipulator in 3D. Okay? So with this one here, speed of the end-effector, well, you can guess that this is going to be this form, and this is correct. You will come up with this equation. And put them together, you will come up with general Jacobi matrix here, and Jacobian not so fast. Look at this one here. This general Jacobi matrix in 3D motion is 3 by n. N is the number of joints. So it may not even be square. So singularity, nothing. I mean, Jacobian may not have determinant itself, period, right? So you cannot talk about singularity and so forth. Well, there are more to it. When you learn more about the degrees of freedom, you can talk about that. But anyway, Jacobi matrix is not square, so Jacobian cannot be defined. So, inverse of this matrix, no way. So you have to use a special technique, should I say, which I'm not going to go into that right now. Probably you will see it next year or something, and to do this kind of things. All right. That's it for this lecture. And next time I will talk about Jacobian one more time from different point of view.